With the MEG, we haven't gone to that stage yet. We're still in the open loop system where we haven't put the feedback. But it's possible to do that. We just are working things out one thing at a time. Here's what we have in the MEG. And here's why we can do it with the MEG, legitimately as proven in physics. In the MEG, suppose I have a toroid coil. A toroid is wound around like this in a circle, but it's wound all the way around it very tightly, and it closes back almost on itself. What happens in a toroidal coil is the magnetic field, the B field, is confined inside the coil. It can't escape outside. Normally the magnetic field spills out all into space. We need to know two things. Magnetic field, any force field, is not a primary field of nature. The primary thing is always a potential, and it's called a magnetic vector potential A. That's the name of it. Magnetic vector potential. Now, a magnetic vector potential is a weird beast. It's got two components, basically. One is swirling. It's a curled component, and we would write that del cross A, and that is what we call the magnetic field B. And normally it hides the other component. It covers it to where we don't see the other component. The other component is one that doesn't have a curl. Doesn't have a curl. It's moving straight. So the curl of it is zero. But it's still a real potential. If you take this toroidal coil, first of all, we had to pay to get that B field trapped. But it's been found by Aharonov-Bohm in 1959 that if I normally have a source of B field, and I just draw a dot here that makes B field, it's actually a dipole, and here's the B field spreading out in space, I know that's a curled magnetic vector potential A that I'm looking at, and it's hiding this other component I can't see. It turns out if you'll take all that B field, all that curl component, and pull it back in and hold it in a little area, localized area, so that it doesn't spill out into space, you reveal outside there that hidden component, the uncurled or the curl-free A potential. So isn't this interesting? If you localize the B field into a little small location instead of spreading through all space, you have all the B field energy you would have had through all space. You got that in your hand in this local space, but outside that you got a whole bunch of extra energy now in uncurled A potential form. Well, A potential is wonderful. In the curl form, it makes magnetic field. So if I've got magnetic field, I got all my curl component down here in this localization zone. And outside here, I have a new component of energy I didn't have to use before in my immediate environment, available. Isn't that interesting? Because it's easy to collect it. All you have to do is change it real fast. The time rate of change, dA dt, produces an E field in the opposite direction from where the A field was going, which direction it was heading. It makes an E field, and the magnitude of this E field that it makes, this electric field, is proportional to how fast you change the thing, the time rate of change. So, now wouldn't it be interesting if I could find a transformer core material and construction which would do localization of the B field? What would I have if I did that? Instead of just looking at the B field in my transformer, I would have the B field now inside the core material. But outside the core material, I would have a new available reservoir of extra energy in my environment. And all I got to do is perturb it, and it'll make electric fields, which come back into the system and introduce real electric field energy into the system, which normally no transformer does. That's what we do with the MEG. We found with this nanocrystalline material they're making for new transformers and all, we found a construction core right off the shelf, type of construction and nanocrystalline material, there's 2 or 3 types that'll do it, that if I make a transformer core material here, I'll draw a simple one. This is just a diagram. It's not exactly the way we structure it. Any source of magnetic field, for example, if I have an input coil here, like this, and I'm paying for the input, all the magnetic field from this coil, all of it, is trapped in this core. It doesn't get out, and there's no spillage out there into space. Interesting. How can I prove that? I put a permanent magnet very tightly across here. North pole here, south pole here. Got to have real good contact, no air gaps of this magnet. It's a very powerful little magnet. It's right across the transformer core material. And then I take an instrument with a field probe to measure magnetic field B, and I put it right on, let's say, that north pole. My instrument measures no magnetic field, or almost zero. It's impossible to get total contact. You will have the tiny, tiny air gap, so you will measure a tiny, tiny field. But essentially a zero magnetic field right on the surface of the magnet. Now that proves that all the magnetic field that normally spilled out of this magnet everywhere has got sucked into this core and is sitting there. When you localize the B field and expose around it that usually hidden, uncurled A potential, that's called the Aharonov-Bohm effect. Aharonov was a student of Bohm. Aharonov. Bohm was David Bohm, of course, as everybody's aware. And in 1959, they published a very formidable and fundamental paper in a physical review series pointing out this effect. When you localize this magnetic field in the space outside this core, not in the core, outside the core, there appears this A potential. But it's the uncurled variety now. It's extra. I didn't pay for it. If you want to put it in proper gauge language, the Aharonov-Bohm effect gauge transforms the space outside the localization area, which means you see additional energy available there in space itself. That's rigorously proven in literature. Don't have to reprove it. 20,000 papers in literature. But it's not in electrical engineering, but it's in physics. The difference here in the MEG is we don't have to pay for what this material is doing. We didn't have to pay to get that extra A potential energy reservoir formed outside the core. That happened free. It's from that regauged space-time, which is a change in that vacuum. It's a result of the fact that this core material will do for free what I got to pay a toroid to do. Only it's free. I don't have to pay for that effect. If I got a toroid, I can get the effect, but I pay for it. I lose everything I'm going to get. I don't have to pay for it in this case. The material does that extra action for me. That's the beauty. Material effects, by the way, are one of those places already recognized in thermodynamics itself as violating the second law of thermodynamics. Material effects, like long-term memory and all kinds of things. Read Prigogine and Condiputi's book, Modern Thermodynamics, that deals with non-equilibrium systems. You will find that that's one of the areas that is known by the thermodynamicists themselves to violate that second law. So I don't have to prove that I'm violating it permissibly. It's already been done by a Nobel Prize winner. So what we have now is, I have an interesting situation. I have what looks like a normal transformer core, but there's a very abnormal thing happening in it. All of the magnetic field B is now confined to the core. And around that, I've got all the magnetic field energy, the swirling energy that I normally have in every transformer. I've got all of that. I haven't lost anything. But in addition, I've got this extra energy reservoir in space just outside the core. And every time I perturb the core, like with my input coil, I put in, clever devil that we are, we put in pulses, sharp rise time and sharp decay time. If I want to get a little bigger E fields, I make a sharper rise time and a sharper decay time. I get an E field one direction one time and the other. And what happens is the space here, I can have as many coils wound on this core as I wish. Let's put an output coil on it, just to say we got an output. And it looks like I got my drawing a little bit reversed, but that's okay. There's an output, and over here I got a big load. But in this space outside the core, I'm going to shade the core here so we can begin to see what this looks like. In this space outside where my uncurled A potential is, and I'm going to put a bar over that A to mean that it's a straight moving A. It's not a swirling A. It's not a magnetic field at all. Every time I shake or perturb this A potential, it makes an E field. E equals minus dA dt. And the sharper the change, the greater the size of the E field. From space around the core, this does not happen in any other normal transformer in the whole world as far as we're aware. From the space outside the MEG, there arises then these tremendously strong E fields which radiate into every coil that's wound on this transformer. So every coil on this transformer that's wound, I could have a dozen coils on here. Every one of them is also, regardless of what other function it's producing, is also an input coil for energy coming in from the vacuum in electric field form, not magnetic field form. The biggest action in the MEG is an electric field transformer, not a magnetic field transformer. And we're using a proven effect, Aharonov-Bohm effect, that 20,000 papers in the literature already tell you happens for real. We didn't dream this one up. We just found how to do it for free. How to get it to happen with the material doing it for us instead of us have to pay a toroid to do it and lose all the advantage. Every coil then has got E field inputs. That's in phase. The funny thing about our output, a normal transformer output will be up towards 90 degrees. It's 85 degrees. It's got some resistance in it, but it'll be like almost pure reactive power coming out of it. That's not true of the MEG. It'll be 2 degrees. It'll be essentially in phase. It's almost pure power, and not a real power, not reactive power. And it's in pulse form. And so what we have to do, we have to add another unit on here, standard technology, to change these pulse forms into a normal kind of power form, like oscillating current or DC current, whatever. So you just go buy that off the shelf from people who are experts and do it very efficiently. But what we really have that's significant, it's not a regular transformer. We have an extra energy input from the environment that we don't pay for. That's the key. Now let's draw the MEG diagram, and it turns out to be just like that crazy heat pump. I have my system called the MEG. I'm going to do the open loop. I'm putting in the operator input. I'm paying for that. Paying the power company, or paying for a battery or something. But now, from the environment, I have this extra input of energy, and I'm going to put the bar over the A, and when I perturb it, it's going to be in dA dt equal minus E. Instead of going out, it's going to come in. So now I have an extra input of energy into my system free from the environment, just for putting in the input I'm putting in. The other part comes along for free. I get that as an extra added attraction. So if I put in one part and I get my input from the uncurled A potential active environment, the E field input, if I get that to be, let's say, 5 parts, be very conservative here. I can make it 10 or 12 or 100 parts, but it'll burn the insulation right off the wire then. So it'll destroy the unit. But suppose I settle for 5, I adjust the rise time and decay time until I get this 5 parts in. Now, coming out, I have input here 6 parts total. The part I put in, I pay for. The 5 parts that the environment puts in, I don't have to pay for. So I have 6 parts of energy coming in here. A normal transformer can be about 85%, 90% efficient. Recapitulating, I pay to input 1 part. The environment is now, by the way we have it adjusted, we make the adjustments in the input until we get this effect, let's say, is putting in 5 parts. And now we have a total of 6 parts, total energy being put in here. Okay, let's suppose this is 90% efficient. Coming out of that then, I'll have 90% of the 6 parts, which is 5.4. So my energy that I'm getting out is 5.4 parts. Okay, what's the COP? I put in 1, I get out 5.4, divide 5.4 by 1, the COP is equal to 5.4. I get 5.4 times as much usable energy out as I get in. This is just an energy converter. Now when I add another stage on here to convert that into a standard kind of power form, either direct current and certain voltage or so forth AC, I will have an inefficiency existed there. Maybe I'll cut this down. Let's do real bad. Let's cut this down to 3. Let's lose 2 points, almost half of it. We didn't have too efficient a conversion, let's say. We were sloppy. We didn't go get the state of the art. We're much better than that. But even with the bad one, once we have it set to run loads, and actually running loads and lights and motors, we're putting in 1 part, we're getting out 3 parts. We have a 3-to-1, we have a 3.0 COP practical. And that's 3.0. This is a standard achievable thing with the MEG. Okay, then the question that's asked, then why don't you guys have this thing on the market in mass production, rolling everywhere? It's a very good question, because let's see why we don't have. What is going on in the MEG that we went through? We pointed out that the E field hits every one of those coils. There's a little bit of out of phasing and everything. They're not all on the same phase. And each coil, once it gets an E field, fires at every other coil and everything's feed forward, feed back. That's a highly nonlinear situation. And that is the devil and all to try to precisely measure. Trying to measure an individual signal in a dense signal environment is not a simple thing. There people can do it, but it requires special instrumentation and highly specialized measurement equipment. Forget your normal oscilloscopes and probes. You can never straighten all of that out. You do it by trial and error and adjust it until it's mostly additive. What we need now is to do all the precision modeling and all the precision work, to work all that out with a math model, to work out the actual measurements and the characteristics of the material, how that affects it and all this. That's 1 year of very hard work. You've got to have 4 specialists in special areas to work with you to do it. We're trying to measure all those exact signals and work out what we would call the transfer function, exact mathematical model for the transfer function of the MEG. If you build those all out of phase so they're subtractive rather than additive, you'll build a worse transformer than a normal. You'll be better off throwing all that away and build a regular transformer. But if you get them additive, you beat the heck out of every other transformer in the world, because it goes way over unity. We don't have good control and good models of all of this. What we have to do is adjust everything by hand, and that's not science. We have to keep tweaking the heck out of it. And so what we have to do is a standard, but very interesting and very dense, highly nonlinear control problem, an adjustment problem. We have to have modeling, full modeling for it. We have to have an Aharonov measurement specialist, Aharonov-Bohm measurement specialist. Those guys are well employed. There's very few of them that know a measurement also. You can get them, but they're expensive. We have to have another person that knows nonlinear oscillation theory, and also we have to have another one that knows nonlinear oscillation control theory. Those are specializations. You don't run down to your local university and your local PhD can do that. The interactions have got to be moved to design and science and modeling rather than fiddling with it. We have a $9 million 1-year job with a team including not only the normal guys, but those 4 specialists we got to hire that are very highly paid, by the way, I might say. And they're fully employed gainfully. They're not looking for a job.
By the way, what voltages are you working with? What level input and what level output? 5 volts, 10 volts?
Well, normally we try to put something that'll power something, so we're going to reduce whatever we come out with the output voltage. We're going to reduce it to like 120 volts or something like that. Now, we can produce 1,000 volts or 5,000 volts out of this thing and burn the insulation right off the coils. Normally, as an input, we'll use a battery, or we put in a circuit in front of it, which is a switching circuit to do the switching to make it oscillate and give us the rise time, get the decay time. So you put in a circuit to do all of that, and you adjust and tweak the circuit for the various tunings you want to do. It's a sort of a tuning nightmare almost to get everything properly tuned. But when you properly tune it, it does produce what I've got on this paper. But you can see right away, this is not a simple problem. I don't go get me some transformer guys and whomp up some of these and go sell them. Now, you got your choice about how you fund this. The normal scientific community is not going to fund it. They say you can't do that. Electrical engineering says you can't do it. Forget it. So what you're going to have to do, you're going to have to go to venture capitalists. It's a mixed bag, a mixed breed. There are some good venture capitalists. There's a whole bunch that ain't too good. You cannot work with, as we discussed before, with a government agency. They'll steal you blind and patent around you all around what you've done. So you're still going to have to go to a risk venture capitalist. You're going to have to convince him that the risk, in fact, justify the investment on the front end. If you look at the risk analysis figures, they're great. How big a payoff is self-powering systems and systems that produce a steady 3-to-1 output electrically? They say once we run it through the hopper the year that we want to do on it, where we have good models that we can design it in advance, we can put the coils exactly like we need them, exactly where we need them, exactly with what orientation and so forth. Once we can do all of that from the front end, we can build the thing straightforward and put it together and it'll work just like that. You've made it a technology and a science at that time, not a twiddle with it research outfit. We have a lab bench experiment that's successful. We do not have a ready for production device that can be cranked all across, by the thousands and put on the market. We're approaching all the control problems first. We have to do all of that first. Now, in the United States, we tend to be stupid a lot of times. We took nonlinear oscillation theory and control of nonlinear oscillation and made them two separate fields. If you use the U.S. controlled system, the guy will have you chasing strange attractors for the next 10 years. If you go to the Russians, they'll laugh like the devil at all of that, and they'll say, there's no problem, even random oscillations we can control straight away with our theory, but they put the two together as one field. Fortunately, their results of their control theory, which is far superior to ours, are now available in books in the West. We have a few people now who understand and are trained in the Russian system. So we would jump all that other stuff and go direct to the Russian control system and use that to begin with. Once we have the math models, we have the phenomenology fitted to it, and we have the ability to design and build and scale up, and it'll work that way with just minor tweaking. At that point, we're ready for production and marketing. We're not right now. We are ready for the final stage of development to go from a lab bench experiment, working, successful, to the pre-production model ready to go into production engineering and production. The beautiful thing that we have a recognized, proven, certified mechanism which does re-gauge that space around where the Aharonov-Bohm is effect, and it's in the literature and proven. I don't have to reprove it. So, is it scientifically proven? Yes, in the literature. Will the scientific community accept it? No. Because what they do is they say, oh no, it's a power problem, that's electrical engineering. Electrical engineering says you can't do that. Now, they have been using the Aharonov-Bohm effect since 1959, but they've been paying for it like in little toroidal coils, not getting it free. And the other thing is, the people who have been using it are people that do itty-bitty quantum mechanical experiments. Nobody has thought to use it in power.
So your general operational control is the square wave or the cycle density?
It's not exactly a square wave. It's a sharp rise time, sharp decay time. That's adjustable. The pulse width and the pulse repetition rate are all adjustable. There are many adjustments you can make. Everything affects this thing that you adjust.
What I'm asking about is your only danger is melting the insulation.
No, the real problem is not that. We can solve that just with the rise time, decay time. And we've got that problem solved. But the problems that are difficult, really difficult, is where you have all these high nonlinearities and feed forwards and feedbacks. You actually have a very dense signal environment right inside this thing. You have to measure individual signals in a dense signal environment. That's a tough job.
But in theory, you could build a system where all of this is automatically calibrated.
Once you have done the technology and the modeling, yes, you can do that. Now, if we want to close loop this system, let's take this same system. Let's put a real efficient. So efficient, I'm going to say it's 1.0 because we can get 0.9 if we pay for real good guys to do it. But for ease of calculation, let's put a feedback system on this thing. And let's say it's 1.0, it's 100% efficient. So I don't have to worry about that figure because this 5.4 might be bigger, see. I'm using my 3 here with what we really got of it in practical after we got the shaping for loads. I'm paying that price. The actual output is 5.4, but I'm only charging the 3 because I'm willing to pay, I know I've got to pay that conversion price. It's not going to be that much, but I'm going to be very conservative here. So I'm going to pay 2.4 points and leave my 3. Okay, with this 100% or nearly 100%, I'm going to feed one part back. I'm going to leave 2.0 as the output. But the one part that I feed back now can remove my generator. And it's furnishing, for part of its output is furnishing that input. This is clamped and governed, so it's not going to run away. Okay, I'm now reduced to 2.0 from what I had been doing that was all the way up to 5.4. But that's free energy. It's coming out, it's coming right out of the environment, and it's continuing, and I'm not paying anything for it. It now is the equivalent of a solar-powered system, or a hydroelectric-powered system, or a windmill-powered system. And its COP now is infinity with a closed loop. Once I disconnect that generator, once I get it going and stable and operating under load, with all the controls working, everything's stabilized out, I disconnect the generator. That's Krone's condition, by the way. Krone laid that down in 1945. The great Gabriel Krone, who built a successful negative resistor and self-powered the network analyzer at Stanford University, laid down the condition for making it self-powering. So we're just using Krone's method. I am not free to name the university that's working with us. We are working with a foreign university. We had to go completely out of the United States before we'd find one that, in addition to non-disclosure, would sign a non-circumvention agreement. An inventor can't work under just non-disclosure. He's also got to have non-circumvention. You must not say that I'm going to change some coils and all and patent this thing all around you and run off with it. So if you have a non-circumvention agreement, you can work with them. We could find no U.S. universities that would work with us under non-circumvention, because they are charged with making patents, and they'll try to out-patent you on your own device. We found one in a nice foreign country, and we're very satisfied with those people, and we're working very close with them. They are deliberately, to be purely scientific, staying independent of us. They will not accept funding from us. They are using their own funding, which is meager, but they're using their own funding, so scientific independence is being maintained. The things that I've described we have to do before we get to ready for pre-production engineering is a minimum of 1 year and a minimum of $9 million. Any way we price it, when we get the people that we have to have, the specialists, the equipment, the new test equipment, the new methods of test, new test guys that do that kind of testing, it's an expensive proposition. It's not cheap. But that's peanuts compared to what we're spending on hot fusion, or what we're spending on all kinds of things. Fuel cells and things like that. They're spending billions of dollars here. This is scalable. This is doable. Now, there's one other way we could do it. We could sell stock and raise stock from investors, and I could make all kinds of songs and dances, and so could the rest of our group. We prefer not to do that. We are seeking one single risk venture partner that we can work with. It's an honest group or people. We can work out a mutual arrangement for both our benefits, and then we can get on with the job. Now, what we refuse to do is turn control over to it. We could have gotten funding if we would surrender control and guarantee it never makes the market. We have no intention of doing that. So we will stumble along until we get funding that we can still guarantee it'll go to market, or we can give it the best shot that human beings can give in the world. We're not going to take something and park it on the shelf and it's just one more system that never is going to make it.